Hello, in this video I'd like to talk about Lagrange polynomials. So given n points in the plane, provided that they satisfy the vertical line test, we can find a polynomial of degree n minus 1 passing through all of these points. And what this actually means is kind of strange from a statistical analysis perspective, right? Imagine that we have some sort of data set that roughly falls along a line, but there's a little bit of noise away from the line. We could find a polynomial, a Lagrange polynomial, that passes through all of those data points perfectly. And yet, this polynomial won't really model the data particularly well. It will just be all over the place and generally zoom up to positive infinity or negative infinity at the ends of the data set. So it models the given data particularly well, but it doesn't really have much predictive power. So it's not really useful from a statistical perspective, other than to demonstrate that having a formula that models a data set perfectly actually isn't particularly useful versus a simpler formula that roughly models the data set. So how can we find these polynomials? Let's do an example. Suppose that I want to find a polynomial passing through the point 0, 1, 1, 3, and 3, 2. So what I'm going to do is I'm actually going to create 3 intermediate polynomials, and we're going to add them together. And each of these intermediate polynomials is going to handle each of these points separately while leaving room for the other 2 points. So specifically, we can define a polynomial p0, and I'm going to want it to be the case that p0 of 0 is equal to 1, and p0 of 1 is equal to 0, and p0 of 3 is equal to 0. So this polynomial would then set the value at 0 to be the value that we want it to be, and it leaves the other 2 values, the value at 1 and the value at 3, equal to 0, so that our other 2 polynomials can take care of them without having to worry about interference from this particular polynomial. Now, how can we find a polynomial that that satisfies these 3 equations? Well, notice here we know that the polynomial is equal to 0 at these 2 points. So that means that our polynomial is going to be of the form x minus 1 times x minus 3. So this polynomial here is 0 at 1 and 0 at 3, but doesn't quite work out that p0 of 0 is equal to 1. p0 of 0 is equal to 3. But that's okay. We can take this polynomial and divide it by 3, and that will leave the polynomial satisfying all 3 of these conditions. p0 of 1 will still be 0, and 0 divided by 3 is 0. p0 of 3 will be 0, and p0 of 0 is going to be 3 divided by 3. And I'm going to write this out as 0 minus 1 times 0 minus 3 in the denominator, so that it's clear that when we plug in x is equal to 0, this whole thing is going to cancel out, and that's kind of how we got that 3 that we wanted to divide by. So this is our p0 of x. Now, what about p1 of x? p1 of x, I'm going to want to handle the value at 1, so I'm going to want p1 of 1 is equal to 3, and I'm also going to want p1 of 0 to be equal to 0, and p1 of 3 to be equal to 0, again, to leave room for the other 2 polynomials. p0 took care of the value at 0, so we don't want to add anything to that. And again, we'll have some polynomial p3, which will take care of the value at 3. So we don't have to worry about that. So how do we find a polynomial that satisfies these 3 things? Well, P1 of x is just going to be, in order to be 0 at 3 and 0 at 0, we're going to want to have an x minus 0 times x minus 3 in the numerator. But, of course, this value isn't going to work out properly. At 1, the current value is negative 3, or yes, negative 2. So that's no good. We need to divide this polynomial by negative 2 in order to get it to work out to, well, then it'll work out to 1, and we need to multiply it by 3. So if we take our polynomial and divide it by 1 minus 0 times 1 minus 3, this now is a polynomial that's equal to 0, 1, and 0. And now we want it to be equal to 3 here. So we can just multiply this whole thing by 3. And this is going to be our P1 of x. And then finally, we want a P3, which is going to be 0 at 0 and 1 and correctly handles 3. And the pattern is exactly the same. You can do exactly the same sort of thing that we did here to find a formula that works out to this. And it's worth noting that these are degree 2 polynomials, right? This is a degree 2 polynomial. This is a binomial times a binomial divided by a number. This is a binomial times a binomial divided by a number times a number. And then P3 is also going to be another binomial times a binomial divided by a number. And so we can actually expand these out, work out what these polynomials are, combine like terms, and that will give us a polynomial that of degree 2, right? Each of these polynomials is of degree 2, and so we can combine those, combine like terms, and we can get a polynomial passing through these 3 points. And this doesn't just work for 3 points. We can, of course, extend this technique to an arbitrary number of points. And again, this isn't particularly useful in terms of modeling statistical data. This is an excellent source of what's called overfitting, where you have fit your data set too well, and because of that, you're missing out on kind of the key trends within the data. But nonetheless, Lagrange polynomials are very useful. They're very useful in terms of thinking about what are the sorts of things we can do with polynomials. Can we get them to pass through certain points? Can we get them to do this particular task? And it's worth noting that Lagrange polynomials are unique. Suppose that we had 2 polynomials of degree 2 passing through these 3 points. Suppose we had one polynomial p and another polynomial q, and they are different polynomials. Well, different polynomials of degree 2 passing through all of these points, then their difference, p minus q, is going to pass through the 3 points 0, 0, 1, 0, and 3, 0. And it's also not going to be equal to 0, because we said that p and q were different polynomials. Well, because this polynomial passes through these 3 points, it must be a multiple of x minus 0 times x minus 1 times x minus 3 in order to have roots at these 3 points. But I also said that p minus q was of degree 2. Well, the only multiple of this degree 3 polynomial that doesn't have degree 3 is going to be the 0 multiple. But, well, we said that p minus q was not equal to 0. So that's a contradiction. So not only is this a way to find a polynomial of degree 2 passing through these 3 points, but in some sense, it's the only way. So thanks for watching, and I hope to see you in a future video.